Hello there, and welcome to the Sleepy Space Channel. The Moon has no air, no magnetic field to hide behind, and no way to send anyone home in a hurry. It is the nearest world to our own, and it is quietly one of the most hostile places within reach of us. The ground is powdered glass that never lost its edge, and it works its way into lungs, seals, and joints. Radiation arrives unfiltered, every hour, at a rate that would spend a career dose in months. Temperatures swing 250 degrees twice a month. The crust still breaks, and when it does, the shaking lasts an hour. Over the next 2 hours, we will take each of those in turn, including the debris we have now started sending there ourselves. If you find these explorations worth your time, a like or a subscribe helps the channel reach others who do. Thank you for being here. But for the next 2 hours, none of this is anything you need to carry. No one is asking you to go. Settle in. Let your shoulders soften. Let your breathing slow. Let the weight of the day fade away behind you. Let's begin. Part 1. The ground underneath. The Moon is the nearest world to our own, and the only one any human being has ever stood on. It hangs about 384,000 kilometers away, close enough that we have already been there, close enough that we are going back. And it is one of the most quietly unforgiving places within reach of us. The danger is not dramatic. It is patient. It works by accumulation, and it begins with the ground. There is no soil on the Moon. Soil is a product of water, of air, of living things breaking rock down slowly and building it back into something soft. The Moon has none of that. What covers its surface is regolith, and regolith is made by breakage alone. Every particle of it was produced by something striking the Moon at speed and shattering what it hit. That layer runs 4 to 5 meters deep across the smooth, dark plains, and 15 meters or more across the ancient, bright highlands, where the bombardment has had longer to work. Below it lies a zone of fractured bedrock reaching down a kilometer or further. Below that, finally, intact crust. The Moon is, in a real sense, a broken world with a layer of its own rubble laid over the top. The particles in that rubble are unlike anything on Earth. When a very small object strikes the surface, it delivers enough energy to melt a tiny volume of rock. The melt splashes outward and welds itself around neighboring mineral grains, and what cools is a jagged, glassy fragment with shards embedded in it. These are called agglutinates, and in a mature patch of lunar ground, they make up 1/4 to 1/3 of everything present. On Earth, a grain of sand is rounded. Water has tumbled it, wind has polished it, chemistry has softened its edges over thousands of years. On the Moon, none of those processes exist. A fracture surface created 100 million years ago is still a fracture surface. The edges stay sharp because there is nothing to blunt them. The fine fraction is the part that matters for a human being. Particles below about 20 micrometers are small enough to hang in the air of a habitat rather than settle. They are small enough to pass through seals that would stop anything coarser. And roughly 1 to 2% of the total mass sits below a single micrometer, which is fine enough to travel to the deepest chambers of a lung and stay there. There is a further complication, and it is one of the more troubling facts about the lunar surface. When a silicate mineral is freshly broken, the atoms at the new surface are left with unsatisfied chemical bonds. On Earth, this state lasts seconds. Moisture and oxygen arrive from the air. The bonds are satisfied, and the grain becomes chemically ordinary. On the Moon, there is no air and no moisture. The bonds stay open. That means a grain of lunar dust can remain chemically hungry for an extraordinarily long time. It becomes a reactive object rather than an inert one. And when it finally does meet moisture, that moisture is likely to be the film on the surface of an eye, or the lining of an airway, or the wet tissue at the base of a lung. The reaction that follows is not gentle. We have a terrestrial analog for this, and it is not reassuring. Freshly ground silica in mines and quarries behaves in a similar way, and the lung disease it produces is one of the oldest recognized occupational illnesses in the world. Lunar regolith is not chemically identical to quartz dust, but the mechanism is close enough that it is now treated as the leading unresolved medical question of any long stay on the surface. What we know about the practical behavior of the dust comes from the small number of people who have worked in it. Their reports are consistent to the point of monotony. The dust got into everything. It coated the outer layers of their suits so thoroughly that white fabric turned grey within an hour of the first excursion. It abraded that fabric, working through the outermost protective layer in places. It found the rotating bearings in wrist rings and shoulder joints, and by the third day of surface work, some of those joints were visibly degraded and harder to turn. It scratched visors. It clouded camera lenses. It defeated the seals on the sample containers. Those containers were designed to hold lunar vacuum all the way back to Earth, and a portion of them arrived having leaked because dust on a sealing surface is enough to break the seal. And it came inside. Every time a crew returned through the hatch, the dust came with them, on the suits, in the seams, ground into the fabric. In the reduced gravity of the cabin, it did not settle to the floor the way it would at home. It hung in the air and moved with them. It produced an immediate and unmistakable smell, which almost everyone described the same way, as something close to spent gunpowder. It irritated eyes. It irritated throats. It made people sneeze. Those symptoms cleared within hours, and no lasting harm was recorded. But the total human exposure to lunar dust in the entire history of the species amounts to about 3 days per person, spread across a handful of people. Nobody has any idea what 300 days would do. That is not a claim that it would be catastrophic. It is a statement about how little we actually know. A permanent settlement makes the arithmetic worse in every direction. On a short visit, the dust is a nuisance you can outlast. On a long stay, it is a slow accumulation you cannot. Every airlock cycle imports more of it. Every traverse across the surface stirs up fresh material and charges it. Every repair carried out on external hardware brings contaminated equipment back into a pressurized space. Filters load. Bearings wear. Optical surfaces cloud. Seals fail slightly earlier than they were designed to. And so dust mitigation is not really a system in its own right. It is a requirement imposed on every other system in the base, permanently, and no fully validated answer to it exists. The best proposals are ingenious. Suit ports, where the suit is docked to the outside of the habitat and the crew climbs into it through the back so that the suit never enters the pressurized volume at all. Electrodynamic dust shields, transparent grids that generate a traveling electric wave across a surface to sweep charged particles off it. Magnetic separation, exploiting the tiny grains of free iron that micrometeorite impacts have scattered through the regolith. Each of these works in a laboratory. None has yet been proven across years of operation in the environment it is meant to defeat. Meanwhile, the ground itself is a strange material to work with. Because the grains touch only at points, and because there is no gas between them, regolith conducts heat extraordinarily badly. It is, by accident, one of the best insulators in the solar system, comparable to the engineered foams we manufacture for the purpose. That is useful if you want to bury something. It is deeply unhelpful if you want to dump waste heat into the ground, which is the first thing an engineer on Earth would think to do. The dust also sticks in a way that resists cleaning. Part of the adhesion is electrostatic because the grains carry charge. Part of it is simple molecular attraction between surfaces in close contact, which becomes significant when the surfaces are irregular and the contact is intimate. Brushing does not remove it. Brushing drives it deeper into fabric and abrades the fabric in the process. And the density rises quickly with depth. The very top layer is loose enough to leave a boot print that will survive for millions of years. A few tens of centimeters down, it is compacted enough that a scoop meets real resistance and a drill needs serious torque. Digging on the moon is harder than the low gravity suggests because the material is packed and interlocked and utterly dry. There is one more property worth knowing, because it explains why the dust is so difficult to detect and so easy to underestimate. Scattered through mature regolith are grains of metallic iron only a few nanometers across, produced when micrometeorite impacts vaporize iron-bearing minerals and the vapor recondenses on nearby surfaces. That nanophase iron makes lunar dust weakly magnetic, and it makes it absorb microwaves efficiently. Those two facts are among the very few practical handles anyone has found for dealing with the material at all, whether by pulling it off a surface magnetically or by heating it with microwaves until it fuses into something solid. It also explains the color. Fresh regolith is lighter. The longer a patch of ground sits exposed, the more nanophase iron accumulates in it, and the darker it becomes. Geologists use that darkening as a clock. A bright ray streaming away from a young crater is bright because the material is new. Given enough time, every bright thing on the moon goes gray. All of which means the first hazard of living on the moon is not something that arrives. It is what is already there, under every boot and against every seal, from the moment the hatch opens. Part 2. The thin wall. Above that ground there is almost nothing at all. The pressure at the lunar surface is about 1/10,000,000,000th of the pressure at sea level on Earth. There is technically an exosphere, and it is worth describing because it is one of the stranger things in the solar system. It contains helium, argon and neon, with traces of sodium and potassium, and the atoms in it are so widely separated that they essentially never meet one another. An atom released at the surface travels a long ballistic arc and comes back down without colliding with anything on the way. It is a gas in name only. The total mass of that exosphere for the entire moon is on the order of tens of thousands of kilograms. That is roughly the mass of the air inside a large building, spread thinly over a surface area comparable to Africa and Asia combined. For every purpose that matters to a human being, the moon is a vacuum. Vacuum does not do what films suggest. A body exposed to it does not burst. Skin and blood vessels are strong enough to contain the pressure inside a person without difficulty. What happens instead is quieter and more specific, and it proceeds in a known order. The first thing that happens is that dissolved gas comes out of solution, because there is nothing outside holding it in. Below roughly 6.3 kilopascals of ambient pressure, the vapor pressure of water at body temperature exceeds the surrounding pressure, and water in exposed tissue begins to turn to vapor. Saliva boils on the tongue. It is not hot. It simply has nothing pressing on it. Soft tissue swells, perhaps to twice its normal volume, held in by skin that is doing exactly what it was built to do. None of that is what kills. The swelling is disfiguring and painful, and, in the short term, survivable. What kills is the lungs running backwards. In normal breathing, oxygen moves from the air in the lungs into the blood because the partial pressure of oxygen is higher on the air side. In a vacuum, the air side is at 0. The gradient reverses. The lungs begin stripping oxygen out of blood returning from the body and venting it, and the blood that leaves the lungs for the brain carries less oxygen than the blood that arrived. Useful consciousness lasts about 9 to 12 seconds. That is not a measure of how long a person can endure it. It is simply the circulation time from lung to brain, and it means the last oxygenated blood reaches the brain, and then no more follows. There is no way to hold a breath through it either. Holding a breath in a vacuum ruptures lung tissue as the trapped gas expands with nothing to contain it. If pressure is restored within about 90 seconds, survival is likely and recovery can be complete. Beyond 2 minutes, it is not. So everything a person does on the lunar surface takes place behind a wall a few millimeters thick. A surface suit is not clothing. It is a pressure vessel with a human being inside it, holding a differential against absolute vacuum for 8 hours at a stretch. It runs at roughly a third of sea level pressure, with a high proportion of oxygen, and that choice is a compromise. Lower pressure keeps the suit flexible enough that the wearer can bend a finger. Higher pressure would be physiologically safer and would produce a garment too stiff to work in. That compromise carries a cost, and the cost is decompression sickness. Dropping from cabin pressure to suit pressure lets nitrogen dissolved in the body come out of solution as bubbles, exactly as it does for a diver ascending too quickly. The countermeasure is a pre-breathe, hours of breathing pure oxygen beforehand to flush nitrogen out of the tissues before the pressure drops. It is tedious, it eats into the working day, and it is not optional. Shortening it produces joint pain, then neurological symptoms, then in serious cases collapse, several hours into an excursion in a place where the treatment for decompression sickness does not exist. The wall has to survive the ground as well as the vacuum. The single highest wear component of any surface suit is the glove, and the reason is obvious once stated. The hands do the work. They grip, they talk, they brace against rock, they hold tools. And they do all of that while covered in the most abrasive material any human being has ever worked in. Damage to gloves has been documented from the earliest surface excursions. Outer layers wore through at the fingertips within days. In the training environments used since, repeated work in pressurized gloves has caused fingernail delamination because the hand presses against the rigid structure of the glove with every grip. The glove is simultaneously the most mechanically stressed section of the pressure envelope and the section most exposed to the material most likely to wear it away. A habitat faces the same problem written larger. A pressurized volume on the lunar surface is holding roughly 1 atmosphere of difference against nothing at all, continuously, for years. There is no relief from the environment. There is no atmosphere outside to slow anything down, no water table, no weathering, no gentle conditions of any kind. And the environment is actively working on it. Dust settles on and into every seal. Temperature swings of 250 degrees cycle through the structure twice a month. Ultraviolet light, unfiltered by any atmosphere, degrades polymers and coatings on a timescale of months. Radiation slowly embrittles materials from the inside. Polymers in vacuum lose their plasticizers by evaporation and stiffen over time, which narrows the list of materials that can be trusted in a long-duration seal far more than it first appears. There is also a phenomenon with no terrestrial equivalent, called vacuum welding. On Earth, Every metal surface carries a thin oxide film formed on contact with air, and that film is what allows two metal parts to touch and then separate. In vacuum, freshly exposed metal has no such film. Two clean metal surfaces pressed together can bond directly, atom to atom, because there is nothing between them to prevent it. Mechanisms that must move repeatedly on the lunar surface have to be designed around this, and it is not a theoretical concern. And heat has nowhere to go. Convection does not exist without air. Every watt generated inside a suit or a habitat has to be moved by a pumped fluid loop and then radiated away into empty sky. There is no passive cooling anywhere on the moon. A person sealed inside a suit that has lost its cooling loop overheats in a place where the ground outside might be 120 degrees Celsius or minus 130, and neither of those temperatures helps at all. Every opening in that wall is a compromise as well. A hatch has to seal against vacuum, and it has to be operable by gloved hands in a hurry. A window has to hold pressure and stay optically clear while ultraviolet light and micrometeorite pitting work against it. Every electrical feed-through, every fluid line, every antenna mount is a place where the inside meets the outside, and every one of them is a place where the seal is a designed object rather than continuous material. A habitat's real vulnerability is not its walls. It is its penetrations, and a base has hundreds of them. Leak detection, therefore, becomes one of the quieter arts of living in a sealed volume. A large breach announces itself immediately, and the response is rehearsed and fast. The difficult case is the slow one. A pressure loss of a fraction of a percent per day sits close to the noise floor of the instruments and close to the ordinary variation caused by temperature. It can run for weeks before anyone is confident it is real, and finding its source in a structure full of cable runs and equipment racks is genuinely hard. Crews on long-duration spacecraft have spent months chasing leaks of exactly this kind. The suit adds a further constraint that shapes the whole working day. Its consumables are finite and small. Oxygen, cooling water, carbon dioxide absorption capacity, and battery power all run down together, and the excursion ends when the first of them does. That gives a working envelope of roughly 8 hours, minus the time to get out and the time to get back, minus a reserve held for contingencies. Everything a crew wants to accomplish outside has to fit inside that envelope, and the envelope does not stretch. The exosphere, incidentally, does one lovely thing. Sodium and potassium atoms in it are struck by sunlight and re-emit that light, and the pressure of sunlight pushes them gently away from the sun. The result is a faint tail of glowing sodium streaming away from the moon, hundreds of thousands of kilometers long, detectable from Earth with the right instruments. The moon has a tail, like a comet, made of almost nothing. It is also so thin that a single lander's exhaust can multiply the local density by orders of magnitude, and it takes weeks for the disturbance to fade. We arrive, and the atmosphere of the moon notices. Part 3. The sky that never closes. Earth protects the ground beneath it twice, and both defenses are invisible from where we stand. The first is magnetic. The planet's field extends far out into space and deflects the great majority of charged particles arriving from the sun and from the galaxy beyond it, steering them around us. The second is simply air. Standing over every square meter of ground on Earth is about 10,000 kilograms of atmosphere. Measured as shielding, that is the equivalent of several meters of concrete, and it absorbs nearly everything the magnetic field misses. The moon has neither. It carries only weak, patchy remnants of crustal magnetism in scattered places, and it has no atmosphere worth the name. Radiation arrives at the lunar surface essentially unweakened from every direction, without pause. There are two populations to account for, and they are different in almost every respect. The first is galactic cosmic rays. These are the bare nuclei of atoms, accelerated somewhere in the galaxy to speeds approaching that of light, arriving from all directions at a low but absolutely relentless rate. Most are hydrogen nuclei, a few percent are helium, and roughly 1% are heavier things: carbon, oxygen, silicon, iron. That 1% does a disproportionate share of the damage. The energy a charged particle deposits as it passes through matter scales with the square of its charge, so an iron nucleus with 26 protons deposits several hundred times what a single proton does along the same path. It does not scatter its damage gently. It leaves a track of dense ionization straight through whatever it crosses, and every cell along that track is either killed or damaged. The intuitive response to radiation is to put mass in front of it, and here that intuition partly fails. A thin shield does not stop a relativistic iron nucleus. It fragments it. The nucleus shatters against the shield and produces a shower of secondary particles that spread out behind it, and that shower can deliver more dose to what lies beyond than the original particle would have. Meaningful reduction requires enough mass to absorb the whole cascade, which means meters of regolith rather than centimeters of aluminium. There is no light solution. The measured dose rate on the lunar surface is roughly 2 to 3 times what is recorded aboard a station in low Earth orbit, which sits inside the protection of the planet's magnetic field. Expressed against ordinary life, it is something on the order of 200 to 300 times the natural background at Earth's surface. Put plainly, a person living on the Moon accumulates in a single day roughly what a person at home accumulates in most of a year. That is not a dose that causes immediate harm. Nobody falls ill from it. It is a slow, cumulative, entirely unavoidable accounting, expressed as an increase in lifetime cancer risk, with additional concern for the central nervous system, for the cardiovascular system, and for the lens of the eye, where cataract formation is one of the better documented consequences of heavy iron exposure. Career dose limits are set against an acceptable increase in that risk, and on the lunar surface, depending on shielding, a person reaches the limit in a matter of months to a couple of years. The second population behaves entirely differently. Solar particle events are bursts of protons accelerated by activity on the Sun, and they arrive with very little warning. Most are minor and pass without consequence. A small number are not. Events have been recorded that would have delivered to an unshielded person standing on the lunar surface a dose sufficient to cause acute radiation sickness within hours. Nausea first, then suppression of the immune system, then bleeding, then in serious cases death within weeks. One such event occurred in the window between two of the crewed lunar landings, striking a surface that happened at that moment to be empty. Had the timing fallen differently, the crew on the surface would have had minutes to reach shelter, and no shelter to reach. This is why every serious plan for a lunar base includes a storm shelter. It is a small, heavily protected volume, usually buried under 2 meters or more of regolith, sometimes with the base's stored water and waste built into the walls because hydrogen is efficient at slowing neutrons. The crew can reach it quickly and occupy it for hours or days while an event passes. The shelter then defines the geometry of everything else. Nobody can travel further from it than they can return within the warning time. The warning time for a fast event is on the order of tens of minutes, and the return has to include getting a rover back, getting through an airlock, and getting inside. In practice, this means that a base is not a base with an area around it. It is a base with a radius, and the radius is set by radiation rather than by anything a crew would choose. There is a further problem underground, which is that dose does not simply fall to zero as you dig. Cosmic rays striking regolith produce secondary neutrons, and neutron production peaks at a certain depth before the total dose finally declines. Shielding is therefore not a simple matter of more is better. There is a shallow depth at which you are worse off than at the surface, and the correct answer is to go deeper than that. It is worth pausing on what the heavy nuclei actually do inside a body, because it is unlike anything terrestrial radiation medicine was built around. An X-ray deposits its energy diffusely, spread thinly across many cells, and the body is fairly good at repairing that kind of scattered damage. An iron nucleus does the opposite. It drills a narrow corridor of concentrated ionization through tissue, and along that corridor, the damage is dense enough that the cell's repair machinery cannot keep up. Both strands of a DNA molecule may be severed at the same point, which is the hardest kind of break to mend correctly. The concern about the nervous system follows from that geometry. Nerve cells are not replaced, so damage to them accumulates over a lifetime rather than being repaired by turnover. Animal studies of heavy ion exposure have found measurable changes in behavior and in the structure of neurons at doses comparable to those a long lunar stay would deliver. Whether the same applies to human cognition over years is not known, and it is one of the more uncomfortable open questions in the field. There is also an interaction that makes the accounting worse rather than simply additive. Unloading the body, as reduced gravity does, appears to impair some of the cellular processes involved in repairing damage. If that holds, then radiation on the moon is not simply radiation plus low gravity. It is radiation delivered to a body that is less able to recover from it. The sun's own cycle complicates the picture in both directions. At solar maximum, particle events are more frequent and more severe, so the risk of an acute exposure is at its highest. But the enhanced solar wind at maximum also pushes back against galactic cosmic rays and partially excludes them from the inner solar system, which lowers the background dose. At solar minimum, the opposite holds. Events are rare, and the steady background is at its worst. There is no good time to be on the moon. There are only two different kinds of bad. Electronics suffer too, in a way that is easy to overlook. A single passing particle can flip a bit in a memory cell, and at lunar dose rates, this happens often enough that every computer on the surface must be built with redundancy and error correction as a baseline assumption rather than an added precaution. The same particle flux that slowly damages a person is continuously corrupting the systems keeping that person alive. And the far side introduces its own wrinkle. The radiation environment there is much the same. What differs is that a crew on the far side cannot see Earth at all, because the moon keeps one face turned toward us permanently. Any warning of a solar event has to arrive through a relay satellite. A relay outage during an event is not an inconvenience. It is the difference between reaching the shelter and never knowing there was a reason to run. There is one small mercy in all of this, and it is a strange one. In a few scattered places, the moon's remnant crustal magnetism is strong enough to deflect the solar wind locally. Those patches are visibly brighter than the ground around them, because the darkening that normally comes with long exposure has been slowed. They are called lunar swirls, and they are the only naturally shielded ground on the moon. They are also far too weak to protect anything. A person standing in the middle of one would be measurably no safer. They are a reminder of what a magnetic field can do, written faintly on a world that lost its own a very long time ago. Part 4. The Long Day and the Longer Night. The Moon turns once for every orbit it makes of the Earth, which is why we only ever see one face of it. The consequence at ground level is that a day on the Moon lasts a month. A point on the lunar equator sits in continuous sunlight for about 14.5 Earth days, and then in continuous darkness for about 14.5 more. There is no atmosphere to carry heat from the lit side to the dark side, and the regolith beneath conducts heat so poorly that it barely moves downward either. The surface temperature is therefore governed almost entirely by one question, which is whether the sun happens to be above the horizon. At the equator, noon reaches roughly 120 degrees Celsius, well above the boiling point of water. Night falls to about -130. That is a swing of 250 degrees, twice a month, permanently. And the transition is not the gentle thing an evening on Earth is. Our own sunsets are slow because the atmosphere scatters light around the curve of the planet and holds warmth for hours after. On the Moon, when the terminator passes, the temperature falls away within hours. There is nothing holding it up. The consequences are structural long before they are biological. Every material expands and contracts across that range, and different materials do it at different rates. Joints between dissimilar metals work themselves loose over enough cycles. Lubricants that flow freely at noon become solid at midnight. Seals harden, soften, and harden again. Adhesives fatigue. Batteries lose a large fraction of their capacity in the cold and degrade permanently in the heat. Thermal cycling fatigue is one of the main reasons hardware sent to the lunar surface has historically had short design lives. A machine intended to work for a few weeks can be built to survive one or two of those cycles. A settlement is being asked to survive several hundred. The power problem is more immediate and less forgiving. Solar arrays produce nothing at all for 14 consecutive days. That is not a dip in output. It is zero for 350 hours. Storing 2 weeks of continuous power for a crude base in batteries is not a realistic proposition by mass. The batteries required would weigh substantially more than the habitat they were meant to keep alive, and they would have to be launched from Earth and landed intact. So the options narrow to two. The first is to stop depending on sunlight altogether. Compact fission surface power removes the day-night problem entirely, produces heat as well as electricity, and is indifferent to where the sun happens to be. It is the leading approach for exactly that reason, and it comes with its own considerable engineering and political weight. The second is to move. The Moon's spin axis is tilted by only about 1.5 degrees relative to its orbit around the Sun, which is almost nothing. At the poles, that means the Sun never climbs far above the horizon and never sinks far below it. On certain crater rims and high ridges, the geometry produces illumination for 80 or 90% of the year. These are called peaks of near-eternal light, and the phrasing is careful because none of them is permanently lit. Even the best of them go dark for stretches of several days at a time, and a base sited there still needs to survive those stretches on stored power. Which brings us to a separate problem that is often folded into the first, and should not be. Generating power through the night and surviving the night are different challenges. Keeping a habitat and all its systems above their minimum survival temperature through 350 hours of darkness consumes a substantial fraction of whatever power is available. Every fluid line that must not freeze is a continuous load. Every mechanism that must remain operable is a load. Every instrument with a lower temperature limit is a load. Heating is not a comfort function on the Moon. It is a survival function, and it runs constantly through the coldest half of every month. Robotic missions have been lost to precisely this. A lander sets down, works well, and then simply does not wake up when the sun returns, because something inside it cooled past a limit during the night and did not survive being that cold. The opposite problem is stranger, and it catches people out. Getting rid of waste heat during the lunar day is harder than it sounds. A radiator works by seeing something colder than itself and emitting toward it. During lunar day, a radiator lying flat on the ground sees a surface at 120 degrees Celsius. It is trying to dump heat into something hotter than the heat it is trying to dump. It does not work at all. Radiators on the lunar surface have to be mounted vertically, edge-on to the sun, aimed at the black sky rather than the bright ground, and even then, their performance falls sharply as the sun climbs. The hottest part of the lunar day is also the moment when the ability to shed heat is at its weakest, and the base is at its most crowded with running equipment. Dust makes both directions worse. A layer of fine regolith on a radiator surface changes how efficiently it emits. A layer on a solar array reduces how much light it collects. Measurable losses appear within a single mission, and there is no rain on the moon, and never will be. There is a second, quieter penalty attached to the long night, and it is one of scheduling rather than physics. Almost everything a crew wants to do outside is easier in sunlight. Surveying, driving, construction, sample collection and repair all depend on being able to see, and portable lighting on a surface with no atmosphere illuminates a narrow cone and leaves everything outside it in absolute black. So the productive half of the month is the lit half, and the dark half is spent maintaining, waiting, and consuming stores. A lunar base does not run at a steady rate. It runs in a fortnightly rhythm imposed from outside, and every schedule slip pushes work into a window that is closing. Thermal design also constrains where things can be placed relative to one another. A radiator needs a clear view of cold sky and must not see the hot ground or a neighboring structure. A solar array needs a clear view of the low sun and must not be shadowed by anything, including the terrain. A storm shelter needs to be close. A landing pad needs to be far. Each of those requirements pulls the layout in a different direction, and on a polar ridge only a few hundred meters wide, they cannot all be satisfied. There is, however, one elegant escape from most of this, and it sits about a meter below the surface. Because regolith is such an extraordinary insulator, the enormous temperature swing at the top barely penetrates. By a depth of roughly 1 meter, the temperature is nearly constant all year, sitting somewhere around -20 degrees Celsius and staying there. The 250-degree cycle simply does not reach that far down. Burying a habitat therefore solves the thermal problem and the radiation problem and the micrometeorite problem simultaneously, with a single action, using material that is already on site and free. This is why nearly every serious long-duration lunar architecture is subsurface in one way or another, whether by excavating and covering, by piling regolith over an inflated structure, or by moving in somewhere that is already underground. And the moon does have somewhere already underground. Ancient basaltic lava flows left hollow tunnels behind them, and some of those tunnels have partially collapsed roofs that open onto the surface as deep circular pits. Gravity measurements and the geometry of the pits suggest that some of the intact tunnels are enormous, hundreds of meters across, far larger than anything comparable on Earth, because lunar gravity allows a wider span to hold itself up. A lava tube offers stable temperature, several tens of meters of overhead rock against radiation and impacts, and a floor that has not been disturbed in billions of years. It is, by a considerable margin, the most attractive real estate on the moon. It is also entirely unexplored, and nobody has yet measured whether those roofs would stay up during an extended moonquake. Above ground, meanwhile, the light itself is different. There is no atmosphere to filter it, so ultraviolet exposure at the lunar surface is far higher than anywhere on Earth, and it degrades polymers, paints, and optical coatings on a timescale of months. And shadow is absolute. With nothing to scatter light sideways, the boundary between sunlit ground and shadowed ground is a line a few centimeters wide, across which the temperature can differ by more than 200 degrees. A shadow on the moon is not dim. It is genuinely black, and a suit glove can touch both sides of that line within a single task. Part 5. What falls from above? The Earth is struck constantly and notices almost none of it. Somewhere between 40 and 100 tons of material arrives at the top of our atmosphere every day, and nearly all of it never reaches the ground. Objects arriving at tens of kilometers per second meet enough air high above the surface to heat and disintegrate before they get anywhere near a person. What we see of that process is a brief streak of light, and we call it beautiful. The moon has no such filter. Every particle arrives at full velocity, carrying its full energy, all the way to the surface. There is no upper atmosphere to burn anything up in, because there is no upper atmosphere. The flux is dominated overwhelmingly by very small things. Grains in the microgram range strike any given square meter of lunar surface on a timescale of days to weeks. Particles of a milligram are rarer. Objects of a gram or so strike a given square meter roughly once in many thousands of years. Written out like that, the numbers sound reassuring. What makes them matter is speed. Impact velocities on the moon run from about 2.5 kilometers per second at the very low end up to 70 or more, with an average for ordinary sporadic material of around 20. At 20 kilometers per second, a particle carries roughly 200 times the kinetic energy per unit mass of a rifle bullet. A milligram of rock arriving at that speed can punch cleanly through thin metal, and does. For a suit or a habitat, this becomes a problem of probability rather than certainty. The chance that any particular excursion is interrupted by a penetrating strike is genuinely small. The chance that a base with several hundred square meters of exposed pressurized surface over a decade of operation experiences at least one is not small at all. That is simply what happens when you multiply a small number by a large area and a long time. The engineering answers are two. The first is the bumper shield, a thin sacrificial layer standing off a short distance from the pressure wall. An arriving particle strikes the bumper and is vaporized by its own energy, and what continues onward is not a bullet, but an expanding cloud of gas and fragments spread across a wide patch of the real wall behind it. The energy is the same. The concentration is not, and concentration is what does the damage. This is the standard approach for spacecraft, and it works well. The second, and the more practical answer for a surface base, is simply to pile several meters of regolith on top. It is heavy, it is free, it is already there, and it solves radiation and temperature at the same time. The trade is that emplacing it requires excavation equipment operating in the most abrasive material in the solar system, which is a problem discussed elsewhere in this survey. A suit cannot carry either solution. What it can do is be built in many layers, so that a small penetration produces a slow leak rather than an immediate breach. That is the actual design philosophy, not to be impenetrable, but to fail slowly enough that the wearer has time to notice, seal, and return. There is a second effect of all this bombardment that is easier to overlook, and it may matter more for daily life than the direct strikes do. Every impact throws material outward. On Earth, ejecta from a small impact travels a short distance and settles because air resistance takes its energy away quickly. On the Moon, there is no air to slow anything, and gravity is 1/6 as strong. Ejecta from even very small impacts follows clean ballistic arcs, and those arcs are long. Fine particles routinely travel tens of kilometers from a small strike. Larger events send material hundreds. The result is a continuous, gentle rain of secondary material falling across the whole surface at all times, and it acts as a slow sandblasting process on everything exposed. Optical surfaces degrade. Reflective coatings pit. Solar arrays lose transmission year by year. Mirrors placed on the surface decades ago have measurably lost efficiency, consistent with exactly this combination of dust accumulation and micrometeorite pitting. Nothing left outside on the Moon stays as it was. Secondary impacts, material thrown up by a primary strike and coming back down somewhere else, outnumber primary impacts by an enormous factor. They dominate the slow reworking of the top layer of the surface, a process usually described as gardening. Given enough time, the upper meter of the Moon is turned over completely, grain by grain, by nothing but falling debris. The gardening has a further implication for anything a crew builds. A structure standing on the surface is not sitting on stable ground in the way a foundation on Earth sits on bedrock. It is sitting on a layer that is being slowly stirred from above, at a rate too small to see, but large enough to matter across decades. Cables laid on the surface become buried. Markers become indistinct. Fine material creeps into gaps. It also means that the surface has a memory, and the memory is fragile. A bootprint left on the Moon will survive for millions of years, because there is no wind and no water to erase it. But it will not survive forever, and what erodes it is exactly this rain of secondary particles, softening the edges grain by grain over geological time. The footprints left by the first people to walk there are already very slightly less sharp than they were. Then there is the question of streams. The Moon travels alongside the Earth, and it passes through the same trails of cometary debris that produce our meteor showers. During a stream crossing, the flux of material at the lunar surface rises measurably above background for hours. Impact flashes on the Moon's night side have been recorded from Earth during these periods, bright enough to see with a modest telescope, corresponding to objects weighing a few kilograms, striking hard enough to glow. Dedicated monitoring programs now record dozens of such flashes every year. The rate is not high enough to make surface activity impossible. It is high enough that mission planners treat known stream crossings as elevated risk windows and consider restricting excursions during them, in the same way that a construction site pauses work when the wind gets up. There is one further consequence of the low gravity worth stating. Escape velocity at the lunar surface is only about 2.4 kilometers per second, which is slow by impact standards. That means a meaningful fraction of the material thrown up by any decent-sized impact does not come back down at all. It leaves the Moon entirely. Some of it eventually reaches Earth. There are lunar meteorites in collections on this planet, pieces of the Moon that were launched off its surface by an impact, drifted through space for an unknown length of time, and then fell through our atmosphere as ordinary shooting stars. The Moon has been quietly sending us samples for as long as there has been an Earth to catch them. And there is no terminal velocity anywhere on the Moon, which is a small detail with a real consequence. On Earth, a falling object reaches a speed at which air resistance balances gravity and then stops accelerating. On the Moon, nothing balances gravity. An object dislodged from a height keeps accelerating all the way down, So although it falls more slowly than it would at home, it also never stops speeding up. A tool dropped from a gantry arrives faster than the low gravity leads anyone to expect. There is also a hazard here that has nothing to do with what arrives from space. Anything moving fast across the lunar surface throws material the same way an impact does. A rover, driving at even a modest speed, flings regolith off its wheels in long, clean, unbraked arcs that land many meters behind it, intact and still sharp. On Earth, the same material would tumble a short distance through air and settle. On the Moon it flies. Convoy operations, where one vehicle follows another, have to account for the fact that the leading vehicle is continuously firing abrasive particles at everything behind it. Step back far enough, and the whole surface is a record of this. Every crater is one event. In the bright highlands, the craters overlap so completely that there is no original ground left anywhere at all, at any scale you care to look at. It is all one enormous accumulated bruise, laid down over 4 billion years. And that process has not stopped. It is running now, at the same rate it has run for most of the Moon's history. It only looks like stillness, because a human lifetime is far too short to see it happen. Part 6. The debris we sent ourselves. Everything described so far has been arriving at the Moon for 4 billion years. In the last few decades, something new has been added to it. The Moon is now struck, regularly, by objects that were built. Every mission that reaches lunar space leaves something behind. Spent upper stages that carried a payload out of Earth orbit and had nowhere else to go. Descent modules abandoned on the surface. Orbiters at the end of their fuel. Landers that failed on the way down. Some of these were set down gently and are sitting where they were left. Most were not. Disposal by impact is standard practice, and the reasoning is sound. A spent stage drifting in an unpredictable orbit around the Moon is a hazard to every mission that follows, and there is no cheap way to bring it home. The cheapest place to put it is the ground, and so that is where it goes. There is a case in progress at the moment that illustrates the whole problem neatly, because it is being watched. A spent rocket upper stage, left over from a commercial launch that carried robotic landers toward the Moon, was abandoned in what is called a chaotic orbit. That is not a poetic description. It means an orbit sufficiently influenced by the Earth, the Moon, and the Sun together that its long-term evolution genuinely cannot be predicted with confidence. The object wandered for over a year, while trackers refined its path, and eventually the arithmetic resolved into a lunar impact. The object is a hollow metal cylinder, roughly 12 meters long and 4 meters across, with a dry mass of about 4 tons. It will strike near the Moon's western limb, close to a large crater on the edge of the visible disk, at something like 2.4 kilometers per second. In more familiar units, about 5,400 miles per hour. What makes this event genuinely unusual is that almost nobody knows what it will look like. Impact modeling is built almost entirely on natural impactors. Rock and iron. Dense, coherent, roughly compact objects that behave in a well-understood way when they meet the ground. A spent rocket stage is nothing like that. It is a thin-walled hollow shell, with the mass concentrated at one end and nothing in the middle. It will not deform, penetrate, or transfer energy the way a boulder does. Simulations suggest the resulting plume will differ substantially in shape and in brightness from a natural impact of the same energy. The central spike of ejected material is expected to rise somewhere between 75 and 100 kilometers above the surface, and to remain bright against the dark sky for minutes, rather than the sub-second flash a natural impact produces. It may be visible from Earth with a sufficiently sensitive telescope, though the modeling carries wide uncertainty, and the honest position is that the numbers are optimistic. But the flash is not the interesting number. The interesting number is the range. Modeling of the ejector indicates that resolved particles from this impact will travel ballistic distances of just under 1,000 kilometers from the point of impact. That is a very large fraction of the way across the visible face of the Moon, from a 4-ton object arriving at a speed that is modest by impact standards. There is nothing to intercept any of it. No atmosphere to slow the particles, no weather to bring them down early, no wind to disperse them. They are launched, they follow a curve, and they come down where the curve meets the ground. The implication for anyone living on the Moon is direct, and it changes how the hazard should be thought about. Impact risk on the Moon is not local. An event 1,000 kilometers away, on a body only 3,500 kilometers across, still delivers material to your door. It arrives slower and more dispersed than at the impact site, but it arrives. And unlike natural impacts, which fall at random across the whole surface, artificial impacts are concentrated. They cluster where the traffic is. Traffic clusters where the useful ground is, which is the South Pole. Any settlement will be built in the same region that is receiving the most human-made debris for exactly the same reasons. The problem we already have in orbit around the Earth has a lunar version, and the lunar version has no atmosphere to clean itself with. Debris in low Earth orbit eventually decays and burns up. That is genuinely a self-correcting system on a timescale of years to centuries. On the Moon, nothing decays. Everything that lands stays, and everything it threw stays where it fell. It is worth noting how difficult these objects are to keep track of in the first place. Orbits around the Moon are unstable in a way that orbits around the Earth are not. The lunar crust contains mass concentrations, dense regions buried beneath the great impact basins, and they tug unevenly on anything passing overhead. A low orbit that is left uncorrected does not stay where it was put. It grows more elliptical over months until the low point of the orbit intersects the ground, and then the spacecraft arrives. Almost every uncontrolled object in low lunar orbit ends the same way, given enough time. That instability also makes identification genuinely hard. Objects abandoned in high, chaotic orbits can be lost for years and then rediscovered by survey telescopes as unidentified faint moving points. More than one derelict stage has been confidently attributed to the wrong launch before being reassigned on the basis of a reconstructed orbit. We are not always certain what our own debris is. There is also a subtler kind of contamination. Every artificial impact introduces metals, propellant residues and organic compounds into a surface whose untouched chemistry is one of the main reasons the Moon is scientifically valuable in the first place. We are, slowly, altering the thing we came to study. None of which is to say the event has no value. It has considerable value, and this is worth being fair about. An object of known mass, on a known trajectory, striking a known point at a known time, is a calibration opportunity that almost never occurs. Natural impacts are detected after the fact and their properties inferred. This one can be modeled in advance and then checked against reality, which is how models are actually improved. It also permits a test of impact localization. Any future lunar seismic network will need to identify precisely where an event occurred using signals recorded far away, and that technique can only be validated against something whose location is independently known. This impact provides exactly that. And it will produce a fresh crater on a surface that has been photographed in detail beforehand, with orbital passes both before and after, so that a new feature can be identified and measured against a known energy. That is a rare and useful thing. The plume itself leaves a mark that outlasts the event by a very long time. Ejected material settles in a pattern radiating outward from the impact point, and because that material is freshly exposed, it is brighter than the surrounding ground. Orbital imaging can therefore locate a new crater by its bright rays, even when the crater itself is only a few meters across. Those rays fade over tens of millions of years as exposure darkens them again, which means every bright-rayed crater on the Moon is, in geological terms, recent. There is precedent for using impacts deliberately as instruments. Spent stages have been aimed at the surface specifically so that seismometers already in place could record the ringing. One mission drove an impactor into a permanently shadowed polar crater purely to raise a plume that a trailing spacecraft could fly through and analyze for water. The Moon has been hit on purpose, more than once, in the name of science. The Moon rings for a surprisingly long time when it is struck. Recorded impacts have produced signals lasting tens of minutes because the dry, fractured near-surface material scatters seismic energy rather than absorbing it the way wet terrestrial rock does. A single stage arriving on the far side sets the whole upper crust vibrating for the better part of an hour. The shape of the plume is expected to be lopsided, which is itself a clue worth having. A compact impactor produces a broadly symmetric cone of ejecta, tilted only by the angle of arrival. A hollow cylinder does not. It collapses progressively along its own length as it drives into the ground, delivering its energy over a longer interval and across an irregular footprint, and the material it throws should reflect that asymmetry. Watching how a manufactured object fails on contact is not something anyone has been able to observe directly before. All of that is real, and all of it is worth having. It simply does not change the underlying fact, which is that the Moon is now being struck by our own hardware on a schedule that we set, in places we chose, and that the debris from those impacts travels 1,000 kilometers in a place where nothing ever cleans up after itself. Part 7. 1/6 of your weight. Gravity at the lunar surface is about 1.62 meters per second squared, which is roughly 1/6 of what holds us down here. A person weighing 80 kilograms on Earth would register about 13 on the Moon. This is usually presented as the pleasant part. It is the detail everybody remembers from the footage, the reason astronauts bounced. And it is, in fact, the least understood hazard on this entire list, for a simple and rather startling reason. We have almost no data. Human physiology has been studied exhaustively at 1 gravity because that is where we live. It has been studied extensively at effectively 0 gravity because people have now spent cumulative decades in orbit and the medical record is deep. Between those 2 points there is essentially nothing. The total human experience of 1/6 gravity amounts to a handful of individuals for a few days each, half a century ago, wearing pressure suits and working the whole time. Everything anyone says about the long-term effects of partial gravity is therefore an extrapolation between 2 known points, and nobody knows the shape of the curve that connects them. It might be that most of the protective benefit of gravity arrives at quite a low threshold, in which case the Moon is nearly as good as home, and this hazard largely disappears. It might be that the body's response scales smoothly with load, in which case 1/6 of a gravity provides 1/6 of the protection, and the Moon is very nearly as damaging as free fall. Both are plausible. There is no measurement that distinguishes them. What we do know comes from free fall, and it is not encouraging. Weight-bearing bone loses mineral density at roughly 1 to 1.5% per month in orbit. The loss is concentrated exactly where it matters most, in the hip, the spine, and the neck of the femur, and it does not fully recover on return to Earth, even after years. Some of it appears to be permanent. Muscle atrophies, and the postural muscles go first and go worst, because those are the ones whose entire job is holding a body up against gravity. Take the gravity away, and they have nothing to do. The heart adapts to a lighter workload by becoming smaller and less capable. Fluids shift headward because there is no longer anything pulling them toward the feet. That raises pressure inside the skull, and over months it flattens the back of the eyeball and produces measurable changes in vision, some of which persist long after return. The vestibular system in the inner ear recalibrates to the new environment, and then has to recalibrate again on coming back. Immune function is measurably altered. Latent viruses that the body normally holds in check reactivate. Exercise counters some of this, and not all of it. Crews in orbit spend around 2 hours every day on resistance and cardiovascular work, and that regimen is the reason they come home in the condition they do, rather than something considerably worse. They still come home weakened, and they still need weeks to months to recover. On the Moon, there is at least some load. 1/6 of body weight is not nothing, and walking on the surface genuinely is exercise in a way that floating is not. But bone maintains itself in response to the forces put through it, and 1/6 of the usual force is a much weaker signal than the body is built to expect. Whether it is enough is the open question, and it will remain open until somebody spends a year there and is measured afterwards. Then there is the immediate and practical problem, which is simply moving around. At 1/6 gravity, mass and momentum are entirely unchanged, but traction is reduced 6-fold. A person still has all their inertia and only a fraction of the grip needed to control it. Starting, stopping, and turning all take far longer than instinct expects, and instinct is not something a person can switch off. The crews who worked on the surface converged independently on a loping 2-footed hop, and they did so without being taught. Ordinary walking is inefficient there, because each step launches you off the ground for longer than a stride is meant to last. Above a certain speed, hopping is measurably more efficient, and the body appears to find that out on its own within minutes. They also fell over. Frequently. A fall at 1/6 gravity is slow and gentle, and takes a long time to complete, which sounds entirely harmless, and would be if the person falling were not sealed inside a pressure vessel. They are wearing a rigid helmet with a visor that must not crack, carrying a life support pack on their back, connected by hoses that must not tear, landing on ground made of sharp glass and abrasive rock. Getting back up unassisted in a pressurized suit is genuinely difficult, because the suit resists bending at exactly the joints a person needs to use. A fall on the Moon is not a bruise. It is a low probability but non-trivial chance of damaging the only thing keeping you alive, followed by a struggle to stand. There is a further complication in how a suit sits on the body once weight is removed. A pressurized suit is fitted and trained in on Earth, where its own considerable mass presses down on the shoulders and hips in a familiar way. On the Moon, that mass is still there, but the weight is not, so the load paths change entirely. Pressure points move. Fatigue arrives in different muscles and at different times than training predicted. Crews have described the sensation as wearing something that pushes back rather than something that hangs, and there is no way to fully rehearse it at home. The countermeasure question is open too. Concepts exist for short-radius centrifuges inside a habitat, spinning beds that would deliver an intermittent higher gravity load to a crew member for a period each day, on the theory that the body may need occasional loading rather than continuous loading. It is a reasonable theory. No such device has ever been built and validated in flight, and the underlying question of what dose of gravity is sufficient has never been experimentally posed. Even the sense of taste changes. The headward fluid shift produces a congestion that blunts smell, and smell is most of what we experience as flavor. Crew food is heavily seasoned for exactly this reason. It is a small detail, and it stands in for a larger one, which is that almost nothing about ordinary bodily experience survives a change in gravity unaltered. Distance judgment fails too, and in a specific direction. On Earth, the atmosphere gives us haze, and haze is one of the main cues we use to estimate how far away something is. Distant hills look faint. On the Moon, there is no haze, so everything is equally crisp regardless of range. There is also nothing of known size anywhere in the landscape. No trees, no buildings, no people, nothing at all with a familiar scale attached to it. The result is that distances are systematically underestimated. A crater rim a kilometre away can be mistaken for a low ridge 50 meters off, and a person can start walking toward it with no idea how far they are committing to go. This was reported by more than one surface crew, and it is one of the reasons traverses are planned with such rigid distance limits. Dust behaves differently in low gravity as well. Particles kicked up by a boot or a wheel do not billow into a cloud and drift back down, because there is no air to suspend them. They follow clean parabolic arcs and land intact, and at 1/6 gravity those arcs are long. The rooster tails thrown up behind the lunar rovers landed many meters behind the vehicle, in a neat curve, exactly as physics says they should, and nothing like the way dust behaves at home. And then there is the return, which is the part least often discussed. Anyone who spends a long period on the Moon eventually has to come back to a planet pulling 6 times harder. After months of partial gravity adaptation, that transition is a genuine physiological event, and the countermeasures for it are inherited from orbital experience rather than measured for this case. Beyond that lies a question nobody can currently answer at all. A child conceived, carried and born on the Moon would develop entirely at 1/6 gravity. Bone, muscle, cardiovascular structure and vestibular system would all form under a load the human body has never once experienced in the whole history of the species. Whether such a person could ever safely visit Earth is completely unknown. It may be that they could not. That is speculation, and it should be labeled as such. It is also not obviously wrong, and it is the kind of question that only gets answered by somebody trying it. Part 8. The ground is not still. The Moon is usually described as geologically dead. That description is close enough for most purposes, and it is wrong in precisely the ways that matter to anyone trying to build something there. The evidence comes from a small network of seismometers placed on the surface during the crewed landings and left running afterwards. They operated for about 8 years, and in that time, they recorded on the order of 12,000 events. When those events were sorted, they fell into 4 distinct classes. Deep moonquakes originate 700 to 1,000 kilometers below the surface, roughly halfway to the center. They occur in repeating clusters, at the same locations, tied to the tidal stress the Earth exerts on the Moon as their separation varies through the month. They are frequent, they are predictable, and they are weak. From an engineering point of view, they are almost a curiosity. Thermal quakes are smaller still. They are the crackling of the near surface as it heats and cools through the enormous day-night cycle, rock expanding and contracting, and occasionally slipping. They are audible to instruments and irrelevant to structures. Impact events are exactly what they sound like, and they are the reason the network was so useful. because every impact is a free experiment in seismology. And then there are the shallow moonquakes, which are a different matter altogether. These originate in the upper crust, perhaps 50 to 200 kilometers down. They are far rarer than the deep events. Only a few dozen were recorded across the entire monitoring period. But they are strong, reaching magnitudes above 5 on the scale used for earthquakes, and they have a property that has no terrestrial equivalent. They last an extraordinarily long time. An earthquake of magnitude 5 on Earth shakes for tens of seconds and then dies away, because terrestrial rock contains water, and water-bearing rock absorbs seismic energy efficiently. The vibration is converted into heat, and the ground goes quiet. Lunar rock is bone-dry and heavily fractured, so it does not absorb seismic energy. It scatters it. The waves bounce around inside the fractured upper crust, losing very little, taking a long time to find their way out. Recorded shallow moonquakes continued shaking for more than 10 minutes. Some ran for the better part of an hour. The signal does not have the sharp onset and clean decay that seismologists are used to. It builds slowly to a peak and then fades away over many minutes, like a bell that will not stop ringing. For anything built on the surface, that duration matters far more than the peak amplitude does. Structures and pressure vessels do not usually fail from a single jolt. They fail from accumulated cycles, from being flexed over and over until something that was holding gives up. A 10-minute shaking event at moderate amplitude is a considerably harder engineering case than a 30-second one at higher amplitude, and no habitat, no pressure vessel, and no buried structure has ever been tested against it, because nothing like it exists on Earth to test against. The cause of the shallow events is the more interesting part of the story, and it changes how the moon should be pictured. The lunar interior has been cooling for over 4 billion years. As it cools, it contracts, in the same way that anything does. The crust on the outside cannot shrink smoothly to follow it, because rock is brittle, so instead it accommodates the contraction by breaking. The result is a global population of thrust faults, where one block of crust has been pushed up and over another. From orbit, they appear as lobate scarps, sinuous cliff-like steps a few tens of meters high, running for kilometers across the surface. There are thousands of them, and they are found everywhere. The important detail is their age. Many of these scarps are geologically young. They cut across small craters that themselves cannot be more than tens of millions of years old, which means the faulting happened after those craters formed. In some places, the regolith on the scarp face appears freshly disturbed. Boulder fields at the base of scarps show tracks running down the slopes above them, and those tracks have not yet been erased by the slow gardening of micrometeorite impacts, which means the boulders rolled recently. The total amount of contraction involved is small. Estimates put the radial shrinkage of the moon since its crust formed at something like 100 meters, which sounds negligible until it is expressed as the amount of crustal shortening that has to be taken up by faults, and until it is recognized that the shortening is still happening now. Thrust faulting is not the only tectonic signature either. In some regions there are graben, long straight troughs where the crust has been pulled apart rather than pushed together. Their presence means the stress field across the moon is not uniformly compressional, and that the pattern of where faulting can occur is more complicated than a single global shrinkage would predict. Some of that extension is thought to be very old, dating from a period when the interior was still warming and expanding before the long cooling began. Some of it may not be. There is also the question of how a moonquake would actually be experienced by a person standing on the surface. On Earth, a great deal of what makes an earthquake frightening is sound. The ground roars, buildings groan, windows rattle, and the whole event arrives through the ears as much as the feet. On the moon, there is no air to carry any of it. A shallow moonquake would be entirely silent. The ground would simply begin to move underfoot, and dust would rise from every slope in the landscape at once, and it would go on doing that for a quarter of an hour without a sound. Then comes the part that matters most, which is where the young faults are. A significant fraction of them are concentrated in the South Polar region. That is exactly where every serious settlement plan wants to build, because that is where the near-permanently sunlit ridges are, and where the shadowed ice is. Several of the shallow moonquakes recorded by the old network have epicenters that plausibly associate with that same population of faults. And the polar terrain is steep. Crater walls and ridge flanks in that region have slopes close to the angle at which loose material becomes unstable. Analysis of slope stability there suggests that some of the sites favored for landing and construction are near enough to failure that a moderate quake could trigger landslides. Put those facts side by side. The ground is not still. The shaking, when it comes, lasts unreasonably long by any terrestrial standard. The faults responsible are young and quite possibly active. And they are densest in the one region on the entire moon that is genuinely worth settling. None of this makes a lunar base impossible. Buildings are built in seismic zones on Earth all the time. What it does mean is that the design case is real, that it is poorly characterized, and that the data underlying it is a small set of measurements taken by 4 stations on the near side, half a century ago, and then switched off. Establishing a permanent seismic network is consequently one of the highest priorities in lunar science, and the reason is not academic curiosity. It is that anyone intending to build there is currently working from a dataset that would be considered inadequate for a modest bridge. It is worth appreciating how odd the lunar seismic signal actually looks, because it is one of the more genuinely alien datasets ever recorded. On Earth, a seismogram has a clear first arrival, then a second phase, then a decaying tail, and the timing between those arrivals is how the structure of the interior is read. A lunar seismogram has almost none of that clarity. The scattering in the fractured crust smears every arrival into every other one, so the trace emerges gradually out of the noise, swells and subsides over tens of minutes. Working out what the moon is made of from signals like that took decades and remains contested in places. There is one more thing the shaking touches. The lava tubes described earlier, those enormous hollow tunnels that offer the best natural shelter on the moon, have roofs that have stood for billions of years. They have stood through every moonquake in that time, which is reassuring. But the stability of a lava tube roof at lunar gravity, under an extended seismic load, with a habitat inside it, has been modeled and never measured. The most attractive shelter on the moon has an unverified ceiling, and the Earth itself is part of the mechanism, which is a strange thought to hold. The same tidal pull that raises our oceans flexes the solid body of the moon by about 10 centimeters over the course of each month. We are, gently and continuously, squeezing it. And every so often, deep inside, something slips. Part 9. The Electric Moon. The moon carries a charge, and it does not carry the same charge everywhere. On the day side, sunlight arrives unfiltered, and a portion of it is energetic enough to knock electrons loose from mineral surfaces. Those electrons leave. The illuminated ground therefore loses negative charge continuously and settles at a positive potential, typically a few volts, sometimes several tens. On the night side, the situation reverses. There is no sunlight to strip electrons away, and the surface sits instead in the flow of electrons carried by the solar wind and, for part of each month, by the plasma in the long tail of Earth's magnetic field. The night side accumulates negative charge, and its potential can reach hundreds of volts, or during the magnetotail passage, thousands. Between the two runs the terminator, the line dividing lunar day from lunar night. It is only a few kilometers wide, and across it, the surface potential swings by an enormous amount. Where potential changes sharply over a short distance, there is an electric field, and at the lunar terminator, that field is strong and horizontal. Now consider a grain of dust sitting on ground that is charged. The grain carries charge of the same sign as the surface beneath it, and like charges repel. For a large grain, the repulsion is trivial compared with its weight. For a very small grain, with a large surface area relative to its mass, the repulsion can win. The smallest particles lift off the ground. This is not a theoretical prediction. Crews orbiting the moon repeatedly reported something they had not expected: a faint glow along the horizon in the minutes before local sunrise, a band of light standing above the limb where there was nothing at all that should have been scattering sunlight. Several of them sketched it, independently, and the sketches agree. Instruments placed on the surface later detected fine particles arriving at heights of tens of centimeters above the ground, in the absence of anything that could have thrown them there. Orbital measurements have since found evidence of a permanent, tenuous population of dust hovering above the whole surface, sustained by a combination of impact ejection and electrostatic lofting. The moon, in other words, has a dust atmosphere. It is exceedingly thin, it is densest near the terminator, and it never runs out because the process that creates it never stops. This is the mechanism that turns the dust problem from difficult into unbeatable. Dust that lifts itself does not stay where it was left. Cleaning a solar array does not keep it clean. Parking a rover at a distance from the worksite does not keep it uncontaminated. Sealing a habitat perfectly still leaves every external surface subject to slow accumulation from a source with no bottom. Radiators, optics, antennas, seals, handrails, hatch rims, docking interfaces, all of them, continuously, from a supply that is regenerated by sunlight. And the particles doing the lofting are precisely the ones we would least like to be mobile. Electrostatic lifting works best on grains a fraction of a micrometer across, which is exactly the size range that penetrates deepest into a lung and is hardest to filter out of an air supply. The horizon glow itself remains only partly explained, which is worth stating plainly. The brightness that orbiting crews described appears too great for the quantity of dust that later instruments actually measured hovering above the surface. Either the observations were recording something else, or the models of how much material can be lofted are missing a process. That disagreement has stood, unresolved, for decades. It is a small thing, and it sits at the center of one of the practical problems of living there. The best mitigation anyone has developed works with the physics rather than against it. An electrodynamic dust shield is a transparent grid of conductors laid across a surface, driven so that a wave of electric field travels along it. Charged particles resting on the surface are picked up by the wave and carried off the edge. It has been tested, it works, and it is the leading candidate for keeping solar arrays, visors, camera lenses, and radiators usable. The cost is that it consumes power continuously, forever, on every surface that matters, in a place where power is the scarcest thing there is. The charging has a second consequence, which is discharge. A person walking on the surface is an isolated conductor moving through a charged environment, insulated from the ground by dry regolith, accumulating potential relative to their surroundings. So is a vehicle. So is any piece of equipment on legs. On Earth this happens too, and we notice it as a small spark on a dry day, but humidity in the air bleeds the charge away continuously and keeps the accumulation small. There is no humidity on the Moon and nothing to bleed anything away. Potentials build and stay built. Discharge events become plausible, particularly at the terminator, particularly on the night side during the magnetotail passage, and particularly for anything wheeled and well insulated. A static discharge through a suit's electronics or through a habitat's instrumentation is a failure mode with no terrestrial intuition attached to it at all, and the mitigations are still being worked out. There is one further electrical and mechanical hazard, and it is entirely of our own making. A vehicle landing on the Moon fires its engine into the surface. It does not simply raise dust in the way a helicopter does. So is no air to spread the exhaust, so the plume strikes the ground directly and accelerates regolith particles outward at speeds up to 1 kilometre per second and beyond. That is faster than lunar escape velocity for the smallest grains, which means some of the material a lander throws never comes down at all. The rest travels outward in a nearly horizontal sheet, extending for kilometers, made of the sharpest particles in the solar system, moving at hypersonic speed. A landing near existing infrastructure is a sandblasting event delivered from the side. This is not speculative either. Hardware left on the lunar surface has been examined after a later vehicle landed a short distance away, and it was visibly scoured. Reflective coatings were stripped. Surfaces were pitted. And that was from a landing far enough off that nobody had considered it a risk. As lunar traffic increases, this becomes one of the defining constraints on how a settlement is laid out. Every landing threatens everything already built, which means landing pads, protective berms, and generous exclusion zones stop being refinements and become prerequisites. One partial answer is to sinter the ground rather than pave it. Concentrated sunlight or microwave energy can be used to fuse regolith in place into a hard, glassy crust, and the nanophase ion scattered through the dust makes it absorb microwaves unusually well, which means the material is almost cooperative about being melted. A sintered apron around a landing site would hold the loose fraction down and stop most of the horizontal spray. It requires no imported binder and no imported material of any kind, which is exactly the quality that makes it attractive. And building a prepared landing pad requires operating heavy equipment in exactly the environment that the pad exists to make survivable. That circularity runs through nearly every lunar problem. The tools that would fix the dust have to work in the dust first. The plume erosion problem also scales badly. It grows with the square of the engine thrust, which means larger and more capable landers, the ones a real settlement would depend on, are dramatically worse than the small ones we have flown. A prepared pad reduces the effect by orders of magnitude and is the obvious answer. Somebody still has to build the first one, standing on unprepared ground. There is an additional wrinkle in the timing of all this. The Moon spends roughly a quarter of each orbit inside the long tail of Earth's magnetic field, where the plasma environment is entirely different from the ordinary solar wind. During that passage, the night side surface charges far more strongly than it does at any other time, and the dust behavior changes with it. So the electrical state of the Moon is not simply a function of where the Sun is. It also depends on where the Moon is relative to the planet it orbits, on a rhythm that runs alongside the day-night cycle without matching it. There is a last detail worth holding on to, because it is quietly lovely, and it belongs to this same physics. The permanently shadowed craters at the poles never see sunlight, which means they never charge positive. They sit instead in a persistent, negative state for billions of years without interruption, and that steady charge affects both how dust behaves inside them and how the ancient volatiles trapped there survive. They are the only places on the Moon where the electrical conditions have not changed since the craters formed. Everywhere else, twice a month, the whole surface flips. Part 10. The best address on the Moon. Almost every serious plan for a lunar settlement targets the same region, and it is not the equatorial plains where the first crews landed. It is the South Pole. The reasons are excellent, and every one of them comes with a hazard attached. Start with the geometry, because everything else follows from it. The Moon's spin axis is tilted by only about 1.5 degrees relative to its orbit around the Sun. The Earth, by comparison, is tilted by 23.5 degrees, and that tilt is what gives us seasons. The Moon has effectively none. At the lunar poles, that near vertical axis means the Sun never climbs far above the horizon and never sinks far below it. It circles around, low, close to level, all year. On a sufficiently high crater rim or ridge, that produces something remarkable: illumination for 80 or 90% of the year, with the Sun simply grazing the horizon rather than setting properly. These are called peaks of near-eternal light, and they are the only places on the Moon where solar power comes close to being continuous. Everywhere else, the 14-day night makes solar power impossible on its own. A few kilometers away, the same geometry produces the opposite extreme. Inside craters whose rims are high enough, the low Sun never reaches the floor and has not reached it for billions of years. These are the permanently shadowed regions, and they are among the coldest surfaces known anywhere in the solar system, falling below -230 degrees Celsius, with the very coldest spots down around 30 to 40 degrees above absolute zero. At those temperatures, volatile compounds that arrive by any means at all simply stop moving. Water ice becomes permanently stable. So do carbon dioxide, ammonia, methane, and various sulfur compounds. Comets and asteroids have been delivering these materials to the Moon for its entire history, and the solar wind has been implanting hydrogen in the surface throughout, and in these craters, none of it has ever been able to leave. Power on the ridge. Water in the hole. A few kilometers apart. It is the only address on the Moon that offers both, and it is why the polar region is now the most contested real estate off the Earth. Now turn each of those advantages over. The low sun angle that keeps the ridges lit also means that shadows are enormous and effectively permanent. A boulder 1 meter high casts a shadow tens of meters long. A modest ridge shadows the ground for a kilometer behind it. Because there is no atmosphere to scatter light around, ground in shadow receives essentially none, and the boundary between full sunlight and total darkness is razor sharp. Human vision cannot bridge that contrast, and neither can a camera sensor. Looking toward a low sun, a visor or a lens is saturated by direct light, and the shadowed ground immediately beside it is not merely dark but entirely unresolvable. Navigating terrain in which half of every scene is a featureless black void is one of the genuinely hard problems in surface operations, and the terrain in question is heavily cratered, steeply sloped and covered in boulders. There is a partial mercy here. Some permanently shadowed areas are faintly illuminated by sunlight bouncing off the crater walls above them, a very dim secondary light that sensitive instruments can work with. It has been used to image inside shadowed craters from orbit. It is not enough to see by. Then there is the cold itself. Any machine sent into a permanently shadowed region is operating far below the qualification range of virtually every component that exists. Lubricants seize solid. Batteries deliver almost nothing, because the chemistry that makes them work slows to a halt. Elastomers become glass and crack. Wiring insulation embrittles. Electronics that generate their own heat can hold out for a while, provided they never stop. Anything passive cannot. So every hour spent inside one of those craters is an hour of burning stored energy simply to stay above the point of mechanical failure, in a place with no sunlight to replace what is being spent. Missions into permanently shadowed regions are therefore measured in hours, not days. And the ice is far less convenient than the phrase suggests. It is not a frozen lake. Current understanding is that it is distributed through the regolith as scattered grains and coatings, at concentrations that may be a few percent by weight, mixed into a matrix that at those temperatures has the mechanical hardness of rock. Extracting it means mining. Mining in permanent darkness, at cryogenic temperature, in a bowl that traps any dust raised because there is nowhere for it to disperse to, using machinery that must not warm the deposit enough to sublimate the volatiles before they can be captured. Every one of those constraints is individually manageable. Together, they describe a machine nobody has built. There is also a genuine conflict buried in the resource case. Those deposits are an archive. They record billions of years of what has been delivered to the inner solar system, preserved because nothing has ever disturbed them. Mining them destroys the record. The scientific value and the practical value of polar ice point in opposite directions, and there is no way to have both. It is worth being precise about how the ice got there, because it shapes what anyone would find. 3 processes contributed. Comets and volatile-rich asteroids delivered water directly, in single events spread across billions of years. Micrometeorites brought smaller amounts continuously. And the solar wind, streaming protons into the surface everywhere on the moon, produced hydrogen that combined with oxygen already bound in the minerals to make water molecules in place. Those molecules then hopped across the surface, a little at a time, whenever sunlight warmed them, until some fraction of them happened to land somewhere they could never leave. That last mechanism means the polar deposits are not a single ancient layer, but a long, slow accumulation, sorted by nothing except which molecules got lucky. It also means the concentration is likely to be patchy in ways that are difficult to survey from orbit, so the first serious extraction attempt will involve a good deal of finding out. Communication from the pole is awkward too, for the same geometric reason. Earth sits permanently near the horizon as seen from a polar site, which means a single hill, a crater rim, or a ridge in the wrong direction can block the link entirely and permanently. The standard answer is a constellation of relay satellites in high elliptical orbits, which works, and which adds one more system that must not fail. The high illumination sites are also small. Some of the best of them are only a few hundred meters across. That has 2 consequences. The first is that a base must fit its power, its habitat, its storm shelter, its radiators, its landing pad, and its exclusion zone into an area smaller than a large farm, while satisfying thermal and safety constraints that pull those elements apart. The second is that there are only a handful of such sites on the entire moon, and more than one nation intends to use them. There is a further constraint that has nothing to do with physics. A high illumination ridge is a fixed, finite, non-replicable location, and there is no established framework for who gets to occupy one. The existing agreements governing activity in space were written when the question was theoretical. It is no longer theoretical, and the number of viable sites is small enough to count. And then the faults. The young thrust scarps described earlier are concentrated in this same polar region. The slopes here are among the steepest on the moon. The stability analysis of exactly these crater walls suggests some of them sit close enough to failure that a moderate quake could bring material down. The temperature difference across that region also creates a problem for anything that has to move between the two. A rover driven from a sunlit ridge into a shadowed crater is carrying its own accumulated heat into a place that will strip it away, and then carrying cold hardware back up into direct sunlight a few hours later. Thermal cycling of that severity, repeated on a working schedule rather than a monthly one, is harsher than anything the equatorial day-night cycle imposes. The polar base does not escape the thermal problem. It simply trades a slow cycle for a fast one that the crew controls, which is arguably worse because it happens whenever the work requires it. So the picture resolves into something uncomfortable. The one region that solves power and solves water also concentrates the thermal extremes, the optical impossibility, the awkward communications, the scarcity, and the seismic risk into the same few square kilometers. And a crew working there would be crossing between the two extremes routinely. From a sunlit ridge where the ground is warm to a crater floor colder than the surface of Pluto, in the course of a single drive over a distance you could walk in an afternoon on Earth. Part 11. Nothing comes for free. A settlement on the moon would not really be a building. It would be a chemical plant that happens to contain people. Consider the inputs plainly. A single person consumes roughly 800 grams of oxygen a day, about 2 kilograms of drinking water, and around 600 grams of dry food. Add water for food preparation, for hygiene, for medical use, and for the systems themselves, and the water figure multiplies several times over. A crew of 6 needs a steady, uninterrupted supply of all of it, every day, forever. None of it exists on the lunar surface in usable form. Oxygen is the strange case, because the moon is full of it. More than 40% of regolith by mass is oxygen. A settlement would be standing on an ocean of the stuff. The difficulty is that every atom of it is chemically bound into silicates and oxides, and prying it loose requires either high-temperature reduction using imported hydrogen or molten electrolysis at temperatures well above 1600 degrees Celsius. Both processes work. They have been demonstrated in laboratories using simulated regolith, and the chemistry is not in doubt. What has never been demonstrated is either of them running at scale, in vacuum, on real abrasive feedstock, continuously, with the reliability that a life support chain demands. Hydrogen reduction yields something like 1 to 2% of the feedstock mass as oxygen, which means enormous throughput of the most abrasive material in the solar system to produce a modest amount of gas. Molten electrolysis has a higher yield and produces a metal alloy byproduct that could be used structurally, which is genuinely attractive, but it requires electrodes that survive being immersed in molten silicate, and that is a materials problem nobody has fully solved. So in the near term, the answer is not extraction. It is closure. Recycling everything as completely as possible. Modern spacecraft life support does this remarkably well. Water recovery from urine, from condensate, from hygiene waste runs at around 90% or better. Oxygen is recovered by splitting reclaimed water electrolytically and by processing exhaled carbon dioxide through a catalytic reaction that pulls its oxygen back out. The numbers are impressive, and the engineering behind them is decades of hard-won refinement. It is still not enough. A 10% loss per cycle, compounded over months, is a substantial and continuous demand for resupply. And the systems doing the recycling are the most maintenance-hungry hardware in the whole architecture. Pumps, filters, separators, catalyst beds, membranes, valves. All of them wear. All of them need parts. All of those parts come from Earth. There is also a question of what closure does to the things inside the loop. In a system recycling 90% of its water indefinitely, trace compounds that the recovery process does not remove accumulate. Volatile organics shed by plastics, by adhesives, by equipment and by people themselves build up slowly in the air and in the water, and monitoring for them is a standing task on every long-duration spacecraft. On a base intended to run for years rather than months, that slow accumulation is a design problem in its own right, and one that no closed system has yet been operated long enough to characterize properly. Food closes worst of all. No crewed vehicle has ever grown a meaningful fraction of its own calories. Small crops have been raised in orbit, successfully and repeatedly, and they matter enormously for morale, but they are experiments rather than agriculture. Scaling up runs into every hazard in this survey at once. Plant growth in partial gravity is untested at any scale. Lighting a growing area is expensive in power terms, in a place where power is the binding constraint. Crops are vulnerable to contamination, to radiation, to thermal excursions, and to the failure of any one of the systems keeping them alive. For the foreseeable future, food comes up from Earth. There are two further shortages that are easy to miss and hard to solve. The first is nitrogen. Habitat atmospheres are mostly nitrogen, not because anyone breathes it, but because a pure oxygen atmosphere is a fire risk of the most serious kind. Plants need nitrogen too, in quantity, and the Moon has essentially none. The only local source is trace implantation from the solar wind, at concentrations of parts per million. Every molecule of nitrogen in a lunar habitat would have to be carried there and then, never lost. The second is carbon. Outside the polar volatiles, the Moon has almost no carbon either. Any closed-loop agriculture would have to conserve it with something close to perfect efficiency, or import it, which is the same problem again. Waste heat is a resource question too, though it rarely gets described as one. Every process running inside a habitat produces heat, and all of it has to be rejected by radiators, because there is no air to carry it away and the ground beneath is an insulator. Radiator area is one of the least compressible items in any base design. It scales directly with crew size and equipment load. It cannot be folded away. It has to face cold sky. And it is exactly the sort of large, thin, exposed surface that dust settles on and micrometeorites puncture. A base that wants to grow has to grow its radiators first. And there is the question of what to do with what a crew produces rather than consumes. On Earth, waste disperses. On the Moon, in a sealed volume, every gram of it stays inside the system until something is done with it deliberately. Water is reclaimed from it. Carbon and nitrogen locked in it are too valuable to discard. So waste processing is not sanitation on a lunar base. It is part of the supply chain, running in reverse, which brings everything to the supply line. The distance is about 384,000 kilometers. Everything that is not manufactured on the surface crosses it, at a cost per kilogram that remains extraordinary, on vehicles that sometimes fail. The Moon does hold one real advantage over Mars here, and it is worth giving it proper weight. Launch windows to the Moon are essentially continuous. There is no waiting for planetary alignment, no 26-month cycle. And transit is 3 days rather than 7 months. If something is needed, it can be sent, and it arrives within a week. That is a genuine and significant difference. It does not remove the dependency. It only shortens the loop. And here is where the whole picture sharpens into something specific. A base running at 90% closure with a resupply cadence measured in months has, at most, weeks of margin. That margin is a single number, and it is calculable, and everyone on the base knows what it is. A launch failure removes it. A landing failure removes it. A problem at the pad, a decision made by a government, a solar event severe enough to ground flights for a fortnight, a vehicle that arrives and tips over on landing. Any of these consumes the margin at once, and there is nothing underneath it. No local agriculture to fall back on. No atmosphere to pull nitrogen out of without machinery. No groundwater. No rain. No reserve of any kind that was not carried there deliberately. The base does not gradually decline. It reaches the end of its consumables on a date that can be worked out in advance. That is what makes lunar habitation genuinely different from every frontier that came before it. A settlement in Antarctica, cut off by winter, can wait. It is cold, and it is difficult, and it is lonely, but the air outside the door is breathable, and the ice is water, and the station endures until spring. A ship becalmed can wait. A remote village can wait. A lunar settlement cannot wait, because waiting is precisely the thing it has no supply of. There is a psychological weight to that arithmetic, which is rarely discussed alongside the engineering. Everyone on a lunar base would know the margin figure. It would be on a display somewhere, updating. Living inside a system where the date of your own resource exhaustion is a visible, calculable number is not a normal human condition, and nobody has yet spent a long time doing it. There are partial answers, and they are being worked on seriously. Sintering regolith with concentrated sunlight or microwaves to produce bricks, pads, and road surfaces without imported binder. Additive manufacturing on the surface so that spare parts are printed rather than stocked, which matters enormously when the alternative is holding physical inventory against every credible failure. Extracting polar water for drinking, for oxygen, and for propellant, which would close the largest single mass item at a stroke. Each of these would transform the arithmetic. None of them has been done. And every one of them requires machinery that must survive the dust, the cold, the radiation and the cycling described in the previous parts of this survey, running reliably, in a place where the repair technician is 3 days away and the spare part is on a launch manifest. Part 12. How it actually ends. The hazards in this survey do not arrive one at a time, politely, waiting their turn. They compound. And when people who plan these missions think about how a lunar settlement actually fails, they do not think about single events. They think about chains. Here is one that involves nothing exotic at all. A solar particle event begins. The warning arrives through the relay, and it gives 40 minutes. A crew is out on a traverse, and they are 35 minutes from the shelter, which was inside the limit when they set out. On the way back, a rover wheel bearing seizes. It has been degrading for weeks because regolith works its way into every mechanism eventually, and this one was overdue for service that had been deferred. The crew dismounts and continues on foot, which is slower and which stirs up dust that settles on their suits and into their seals. One of them falls on a slope. The fall is slow and gentle. The way falls are at 1/6 gravity, and it cracks the outer coating of a visor. Not the pressure layer. Just the coating, which now scatters light and makes the low sun harder to see through. They reach the shelter 14 minutes late, having taken a dose that will sit in their career record permanently. And the dust they brought in during the emergency ingress loads the habitat's filters faster than the maintenance schedule anticipated, so that airflow through the shelter begins to restrict on the second day of a 4-day event. Not one link in that chain is unusual. Every single one of them is documented behavior from missions that have already flown. Here is a slower one. A shallow moonquake shakes a polar base for 11 minutes, Nothing fails outright. The structure was designed for it, and it holds. But a fitting on an external coolant loop develops a slow leak, and the fitting happens to be on the shadowed side of the structure. Escaping coolant freezes as it emerges and intermittently seals its own leak, so the pressure signature is erratic rather than steady, and it reads as instrument noise for several weeks. By the time the fault is correctly diagnosed, the loop has been running degraded through a full lunar noon, when radiator performance is at its lowest anyway. A thermal margin that was designed to be comfortable is now gone, and the base is operating with no reserve in the one system that cannot be improvised. And here is the simplest one of all. A resupply vehicle fails during ascent. The next one is 11 weeks out. The crew recalculates its consumables and finds that it is short. What all three of those chains have in common is not the failure. Things fail everywhere. What they have in common is that there is nowhere to go. This is the fact that separates the Moon from every hostile place human beings have ever occupied on Earth. An Antarctic station is isolated for months at a time, in genuine darkness and genuine cold, and the isolation is real. But it sits on the same planet as its rescuers. The air outside the door is breathable. Water is everywhere, in the form of ice. A submarine can surface. A ship can be reached. A mountain camp can be walked down from, slowly and badly, but walked down from. The Moon offers none of that. There is no atmosphere to breathe, no water outside the sealed system, no direction to walk in, and no possibility of improvisation. A return vehicle has to already be sitting on the surface, fueled and functional and tested, or there is no return at all. If a rescue is to be mounted from Earth, it requires a vehicle that already exists, already fueled, already cleared to fly, and it still takes 3 days. Communication, by contrast, is nearly immediate. Radio crosses the distance in about 1¼ seconds each way, so conversation with Earth is entirely possible with a small permanent hesitation built into it. Relative to Mars, where a message takes many minutes and dialogue is impossible, that is an enormous gift. It is also a peculiar cruelty of its own. Every crisis on the Moon happens in front of an audience that can advise in real time and cannot arrive for 3 days. The experts are right there, in your ear, watching the telemetry, and they are as far away as it is possible for anyone to be. There is one advantage the light time does deliver, and it is real. Robots on the lunar surface can be driven directly from Earth, with a lag short enough for a human operator to work through. That is genuinely useful, and it means much of the dangerous work of preparing a site could be done before anybody goes there at all. And then there is the part of this that has nothing to do with engineering. The lunar sky is black at noon. The sun is a hard white disk in it, and the stars are there behind the glare the entire time, and the ground does not change. Nothing grows. Nothing moves that a person did not move. There is no weather, no birdsong, no wind, no sound of any kind that does not come through the suit's own systems. The same view stands outside the window in the 14th hour and in the 400th day. 2 weeks of unbroken light. 2 weeks of unbroken dark. Nothing between them. And from the near side, Earth hangs in the sky and does not move. It does not rise. It does not set. Because the Moon keeps one face turned toward us, our planet sits in the same patch of lunar sky, permanently, wobbling only slightly. A small blue and white circle, showing every ocean anybody up there has ever swum in, all of it 400,000 kilometers away and completely unreachable. Crews who have spent long periods in orbit describe a predictable dip in morale around the third quarter of a mission, when the novelty is long gone and the end is still not close. That effect scales with how impossible leaving feels. On the Moon, leaving is not merely inconvenient. It is a launch. Everything else follows from that. Lighting inside a habitat stops being a comfort feature and becomes a medical system, because without a day and night outside, the human circadian rhythm has to be imposed artificially and maintained rigorously, or it comes apart. Medical capability is limited entirely to what is already aboard. Surgery at 1/6 gravity, in a dust-contaminated environment, with no evacuation option, is an unsolved problem that mission planners describe candidly and without euphemism as accepted risk. And on the far side, there would be people who could not see the Earth at all. The first human beings in the history of the species with no line of sight to their own planet, unable to look up and locate it, needing a satellite even to send word home. Redundancy on the Moon also has to mean something different from what it means in orbit. On a space station, the escape vehicle is docked at all times, checked, fueled and ready, and the crew can be inside it within minutes and home within hours. That single fact underwrites everything else about how risk is managed there. On the lunar surface, the escape vehicle is a rocket. It has to ignite and fly correctly on its first and only attempt, after sitting on abrasive, thermally cycled, electrostatically charged ground for months, exposed to everything described in this survey. Nobody gets to test it beforehand. So the philosophy has to invert. Instead of preserving the ability to leave, a lunar base has to preserve the ability to stay. Every system is duplicated, every consumable is buffered, every failure is designed to be survivable in place, because in place is the only option there is. So the honest measure of the danger is not any single item in this list. It is not the dust, though the dust never stops and never can be fully cleaned. It is not the radiation, though it accumulates every hour without pause. It is not the cold, or the heat, or the vacuum, or the quakes that ring for an hour without a sound, or the debris that arrives from 1,000 kilometers away, including the debris we sent ourselves. It is the arithmetic underneath all of them. On the Moon, there is no margin that the crew did not carry there. And there is no help that is not 3 days out. Every hazard described tonight is survivable on its own, given enough mass, enough power, and enough preparation. That is the genuinely difficult part. Mass, power, and preparation are precisely the three things that are hardest to deliver across 384,000 kilometers of nothing. And so the Moon goes on, as it always has, turning its one familiar face toward us, entirely indifferent to whether we ever come back to stay. It is not cruel. It is simply a place that was never made for us, holding still in the dark while we watch it from somewhere far softer. Let your breathing slow. Let the day settle behind you. Sleep well and good night.